Let's talk now about the structure and composition of the sun. When we think about the sun, we know it's a ball of gas. In fact, it's a ball of very, very hot gas. So hot, in fact, that whenever we're looking at the seeming surface of the sun, we really are just looking at one of several layers of hot ionized gas known as a plasma. But when we dissect the sun in terms of what it's made of, its composition is overwhelmingly hydrogen. At least if we think about it in terms of the number of atoms, hydrogen makes up about 92% of the sun. The next element that you'll find in the sun is helium, coming in at a paltry 7.8%. But helium is a giant compared to whatever's left over. And all of these trace elements are known in astronomy as metals. In other words, we think of any element that is heavier than helium as a metal. Now, all of these metals combined all add up to about 0.2% of the total number of atoms in the sun. That's not a lot, yet even this trace amount of metals makes our sun a metal-rich star. Now let's talk a little bit about the interior structure of our sun. We divide it into roughly 3 layers, or 3 regions, beginning with the core. The core extends out to about 20% of the radius of the sun, and inside temperatures reach about 15 million Kelvin. Now the pressures in the core are unbelievably high, coming in at about 300 billion times the atmospheric pressure that we find here at sea level. But those high temperatures and pressures are exactly what is needed to create the photons that we see from the sun. And we're going to learn more about how the sun produces light a little bit later on. But suffice to say, it is inside the core that the electromagnetic radiation that eventually becomes light is forged. The next major zone is the radiative zone. It extends out to about 70% of the sun's radius. Now, the temperature in this zone cools from nearly 15 million Kelvin down to about 100,000 Kelvin at the very outer edge. Now, in this environment, energy is carried away via a process called radiative diffusion. So as the term implies, we are talking about photons of light radiating away, but they don't travel in a perfectly straight line. In fact, they zigzag in kind of a drunken walk or a random walk through this radiative zone. So light can get bottled up inside the zone for quite some time. As a matter of fact, it can get stuck in there from anywhere to a few 100,000 to even 1,000,000 years. Eventually, that light will stumble out into the convective zone. So the convective zone works very much like the kind of energy transfer that we experience every time we boil water. The energy is carried from the radiative zone out to the photosphere. So by this time, the temperatures have cooled quite a bit. We started out in the core at about 15 million Kelvin, and now we're down to just a balmy 5,800 Kelvin. It's not very hot at all compared to the rest of the sun. Now this is what we can think of as the surface, but it's important to understand that there is no real surface on the sun. Remember, the sun is a plasma. Therefore, if you were to descend onto the surface of the sun, you would find yourself just moving imperceptibly into the convective zone. The reason why we call this the surface is because this is where the sun becomes opaque to light. In other words, we cannot peer through the photosphere and see into the layers underneath. We have to infer them using other techniques. But the major thing here is that this is where light is finally free to escape into space. So let's examine the surface of the sun in some greater detail, and you'll notice that there are these fine-grained structures, and these structures have a name. We call these granules, and they are just tiny. That is to say, anywhere up to about 1,000 kilometers tiny. So we're talking about, let's say, the size of Texas or even the western half of the United States. But anyway, these relatively tiny convection cells bubble up into the photosphere, bringing energy out to the surface. So again, the surface is where we find light emanating from the sun, and you may also notice the presence of the occasional dark spot. These spots have a name. They're called sunspots. I never said they were cleverly named structures, but they are nevertheless slightly cooler regions on the surface of the sun, and we're going to learn a little bit more about that in a moment. But another way to think about the photosphere is that it is really the region where the sun now transitions into its atmosphere. So the lower part of the atmosphere is called the chromosphere. Now it's worth mentioning that in this chromospheric region, or the lower atmosphere, we're only talking about, about 2,000 maybe to 3,000 kilometers in thickness. And yet the temperature, rather than decreasing, increases. So we're recently at 5,800 Kelvin at the photosphere. Now we're up to about 10,000 Kelvin. And that's a little strange if you think about it. I mean, if you were to hover your hand over your stove and raise your hand up, you wouldn't expect your hand to get hotter. You'd expect it to cool down, and that's in fact what happens. Yet strangely enough, for reasons which we don't fully understand just yet, when we get a little bit further away from the sun, the temperature climbs. So this makes our chromosphere hotter than the photosphere. And it's so hot, in fact, that you need to switch into ultraviolet wavelengths in order to make out some of the structures of the chromosphere. However, if you're lucky enough to experience a total solar eclipse, you will find yourself gazing at the entire outer atmosphere of the sun. This is called the corona. And here, temperatures skyrocket up to as much as 1,000,000 Kelvin, and even hotter. So as I like to say, if you get to see a solar eclipse, a total solar eclipse, you will see the sun's corona. But the coolest thing that you'll ever see is also going to be the hottest thing you'll ever see. Anyway, let's talk about that skyrocket jump from 10,000 Kelvin up to about 1,000,000 Kelvin. If we take a plot of the temperature versus the height or the altitude of the solar atmosphere, you notice that somewhere around 2,500 kilometers, we just make a virtually instantaneous jump. So we call this region the transition region, and we're talking about a layer that is maybe only 50 kilometers thick, and yet the temperatures drastically leap from about 10,000 Kelvin up to 1,000,000 Kelvin and higher. It is a remarkable transition, and we don't really understand why it goes so hot so quickly. Now, we don't have to always wait for a total solar eclipse to study the corona. We can examine parts of the corona at very far ultraviolet wavelengths. And you may notice that toward the top of the sun in this image, in this movie rather, there's a great big hole, and there's another hole somewhere at the 2 o'clock position on the western edge or the right-hand side of your screen. So these are called coronal holes, and they're really just regions where the magnetic field lines of the sun are opened. So if you look closely at near the surface of the sun, you'll see these loops, and each of these loops are magnetic field lines. And what they're doing is that they're trapping these ultra-hot gases in this case, in the lower part of the corona, and there are additional loops underneath trapping gases in the chromosphere. But sometimes these magnetic field lines open up into outer space, and when they do, these very hot particles are able to escape, and they form something called the solar wind. So we're talking about a region of the sun's atmosphere that reaches 1,000,000 Kelvin easily, and for this reason we can only view this at far ultraviolet and even in X-ray wavelengths. But those hot gases that are escaping from the coronal holes are escaping through lots and lots of smaller coronal holes as well, giving us a continuous outflow of charged particles from the sun called the solar wind. So these particles are continuously racing away from the sun at about 400 kilometers per second. Or if you like to think about it in terms of miles per hour, it's about 1,000,000 mile per hour wind. And during times when the solar wind blows harder, as we will see, we have to take steps to protect our spacecraft from potential damage. Next, let's talk about what makes the sun shine.
Whoa.